How do spiders cling on the ceiling? The itsy bitsy spider went up the water spout, goes the nursery rhyme. But how exactly does the spider climb such a slippery vertical surface? Now scientists think they have the answer: hair. It's a simple discovery that may someday lead to innovative new technologies and products, ranging from stickier post-it notes to space suits that adhere to surfaces in zero gravity. Using a scanning electron microscope, researchers from Germany and Switzerland discovered small hairs on the feet of the jumping spider, or Varcha arquata. Each of the small hairs is covered in even smaller hairs called setioles, which have unique triangular tips. These tiny setioles, more than 620,000 in all, give spiders their superior ability to climb up water spouts, along walls and across ceilings. The scientists estimated spiders are able to grip surfaces with a force greater than 170 times their own weight. That's like Spider-Man clinging to the flat surface of a window on a building by his fingertips and toes only, whilst rescuing 170 adults who are hanging onto his back, says Andrew Martin of the Institute of Technical Zoology and Bionics in Bremen, Germany, co-author of the study, published in the most recent Institute of Physics journal Smart Materials and Structures. The researchers speculate the force that allows spiders to climb glass and hang on ceilings is something known as the van der Waals force. This form of attraction, based on the positive and negative charges of individual molecules, acts only when molecules of opposite charges are within a few nanometers of one another. The triangular-tipped setioles on spiders' feet are perfectly designed to take advantage of the van der Waals force because they form hundreds of thousands of flexible contact points. Because there are many small contact points, spiders can adjust the number of contacts needed for different surfaces, whether vertical, horizontal, smooth or rough. Though the total van der Waals force on the spider's feet is strong, it is really just the sum of many small attractive forces on each setiole. That makes moving its foot easy. The spider just lifts each setiole one at a time, rather than trying to lift all at once. And unlike many types of glue, the van der Waals force is not affected by the surface or the surrounding environment. This allows for an unusually high degree of adhesion on wet or oily surfaces. Like spiders, insects have evolved with their own climbing strategies, including claws and clamp-like devices on their feet. In addition, insects secrete an oily liquid that gives them extra adhesion. But in spite of these adaptations, most insects have only a fraction of spiders' ability to climb. The American cockroach, for example, can support just 1.5 times its own weight. Even something called the knotgrass leaf beetle can support just 50 times its weight. One other animal, however, has been studied for its advanced ability to hang tight: the gecko, a small lizard common in tropical regions. And like spiders, the gecko uses branched hairs and miniaturized contact elements on its feet to crawl quickly over smooth walls and other surfaces. What scientists have learned from spiders and geckos may have some meaning for scientists working on new materials and products. One possible application of our research would be to develop post-it notes based on the van der Waals force, which would stick even if they got wet or greasy, said Antonia Kessel, lead author of the study. You could also imagine astronauts using spacesuits that help them stick to the walls of a spacecraft, just like a spider on the ceiling, she added.